Okay, so question 9. Three paths A, E, B, and C, D have been constructed to provide access to a lake from a road AC as shown diagram. The lengths of the paths from roads to lakes are shown. Okay, so B is 80, this one here is 200, and then we have CD, which is 200, and we have AE, which is 120. Now, what we can see here is that if I was to draw the triangle ABE, which is a smaller triangle, this is 120 and this is 80. Then I have to draw the triangle ADC, where this is 200. Okay? Now, what we're going to find out next is that this is a common angle. A is the common angle. We know that this one here, ABE, is 90 degrees, same as that angle there. Then by process of elimination, the two of these are similar triangles. These are similar triangles, therefore their sides are in proportion. Therefore we should be able to find out what AD is. Okay, so you can do it two ways. The first way you could say is that this 120 corresponds to the side AD on the other triangle, in between blue and green. Then you could say EB, which is 80, corresponds to the other side, that is 200. So 120 over 80 equals AD over 200. So 120, same as AD, then divided by that, so 200. Okay, so we're going to do next is we can cross multiply this and multiply the 200 up beside the 120, because this 200 can go up here, and when it does it disappears. So now what we have is 200 times 120, and then we're going to divide the answer by 80. And what we get here is 300 meters. AD equals 300 meters. Now remember, 120 of it is already gone. So 120 of it is from A to E. Therefore E to D must be 120 take away from the 300. That gives us 180 meters. Okay, so 180 meters. Okay, so that's question 9. Question 10. Oh, sorry, another way of doing question 9 before I leave. Another way of doing question 9 is to compare directly the sides. Okay, so you can compare that the 80 here turns into 200 here because it's in between green and red. So just divide 200 by 80, and what you're going to find out is that the big triangle is 2.5 times bigger than the small triangle. So if you multiply 120 by 2.5, you would have found out that this side here would have been 300, 2.5 times bigger. And then once again your AE is 120 take away from 300 to leave here 180. Okay, now this one here, A, B, C, D are 4 points on a circle as shown. AD bisects BAC. So where's BAC? BAC. So that means that this angle here is the same as this angle here. They're both the same angle. Show that ADB and ADB being we've got to make sure we know our targets here. So we're just going to put this in red. Want to know that ADB, A to D to B, this one here, is similar. Now similar means a same shape but different size to APC, which is this one here. So let's start off. We have to prove that they have the same angle. Okay, so I'm going to put down going to give them numbers. Call that angle 1, call that angle 2. Okay, and call this triangle ADB, and call this triangle APC. Now what we have is angle 1 equals angle 2. Reason being it's given bisector of an angle, or given AD bisects angle BAC. There's a reason there. Now, is there's an angle standing on the same arc is what we're looking for here now, okay? So if you look at A to B here, there's a theorem in maths that if you have any two angles, any 2 points, and if I draw a straight line to any other point on the circle, and then I draw it going all the way back, the angle has to be the same every time. So this angle 1 here, or angle 3, will be exactly the same angle as this angle I drew here, angle 4. That's called angle standing on the same arc. So you can see that that actually happens here. You can see that it'll happen with this angle here. Look at A and B, and let's draw a blue line here. So see this angle here? That angle there is the same thing as this pink angle I'm about to draw here. So what we can now say is we can put numbers on these, and we can say, look, your angle 3, angle 4. Angle 4 is an APC, so angle 4 equals angle 3 standing on the same arc. Okay, and then finally, what we can say after that is that all triangles have to add up to 180, so we can just call this one angle 5 and call that one angle 6, and then we can say angle 5 equals angle 6. Reason being, three angles in triangle must add to 180. To 180 degrees. Okay, so that's that one there, hence the triangles are similar. Okay, now I'm done that. Show that AC multiplied by BD equals AC multiplied by BC. Okay, so I'm just going to use a bit of color coding on these ones now. So red equals red, then blue will equal blue, and finally purple equals purple. Okay, pick a side AC. AC is in the small triangle, so AC is in between purple and red. It must equal the other purple and red, because remember they're in proportion. So purple and red on this one is AD. And then I'm also going to choose, let me see, PC, because PC is here. So this is the small triangle, or the green triangle, and this one here is the red triangle, which is the bigger one. So on the small one, we're going to choose PC, which is in between blue and purple. Blue and purple is PC. And then on the other one, we'll have to be in between blue and purple as well, which is BD. And then we can cross multiply, and we get AC multiplied by BD equals AD times PC. Okay, so that's that part done. Now we're on to the next part after that. Next question we have here is question 11. It goes, Dara, using a compass straight edge, he bisected this angle here. His construction lines are shown below using dot lines. His points D, E and F are labelled. Dara says that DF equals EF. Explain why he is correct. Okay, so what we're going to do here, DF equals EF. Okay, so what does DF equal EF? Okay, now there's a reason behind this. Now let me show you. If we were doing the construction, okay, so the construction would have liked when we first did it, would have been something like this. We would have measured an arc length. Okay, so we would have measured this arc length here. Okay, we would have drew this like so, and then on the other side we would have went to D using the same arc length, and we would have drawn this mark here. So you can see that therefore if you look at it here, that they're the same distance as each other. They're from the metal part to the pen tip. Okay, so they're actually the same part. Now how to put this into words would be probably the hardest part here. Okay, so what we might say, let's make this smaller. Okay, what we can say is that DF equals EF because F is the point of intersection between two equal length arcs of centers D and F in the construction. Okay, so that's one answer there. Next thing we're going to do is we're going to use some congruent triangles to prove the next part. Okay, now drawing the line segments DF and EF, prove using congruent triangles that BF bisects ABC. Okay, so I have to prove that they bisect. So what we're going to do, just get rid of all this for a minute. There we go. Okay, so I'm just going to prove that these bisect. Okay, so I'm going to finish off a triangle here. I'm going to make this one. Here's this D. There's one triangle there, and there's the other triangle there. Okay, so if we're to put colors on these, okay, what we want to prove is that BDF, the triangle BDF, is congruent to the green triangle BBFE. So this one here, to prove they're the same thing. Okay, so we'll write that down now. Triangle BDF, and over the other side we're going to have triangle BFE, and let's try and prove it. Okay, so we can say first is that put down here, I should put up here, be easier this way. So we're going to try first of all is that DF equals EF, and the reason for that is equal arcs. They're equal arcs of the same construction. Then we can say that BF equals BF because it's a common side. And finally we can say that BD equals BE because they're constructed equally. In the construction, this arc here from B arc into E and B arc into D, they're all constructed equally. Therefore we have SSS, triangles are congruent. Triangles BDF and BFE are congruent. Okay. Proof that BF bisects ABC. So this means, therefore this means, because the triangles are congruent, what that means is that this angle here must equal this angle here. So angle DBF, must equal DBF being this angle here, guys, and the other angle being EBF equals angle EBF. Hence, this line BF in the middle cut it in half into two equal angles. Hence BF bisects angle ABC. Okay, moving onwards and upwards. The diagram shows a square drawing all its axes of symmetry. Now, axis of symmetry basically means that you can fold it on top of itself, okay? So a square would have, you could fold it this way, where you're basically folded on top of each other like this. Then you could have another way. You just have a straight dead center, where you're just folding one over the other. You have it go dead center again, where you're folding this way over this way. You have it from the other side to the other side like this. Okay, so there you go. So that's all our axes of symmetry there. Just draw them in. Now, each of the four diagrams, we can see here, just extend this. Now, what we can see here, okay, so we have F here, and it's undergone some transformations, okay. So if I was to draw in almost like an XY axis like this, and this is the XY axis for the first one, what we can see is that if this was 0, 0 in the center, 0, 0 here, okay, and there's a match on this red point here. This red point here would be the point 3, 6, and it then turns into the point -3, -6. And what we can see happening there is that it goes straight through the origin. Okay, I'll do this by dotted lines. It goes straight through the origin, down 3, down 6 across 3, down 6 and across 3. Take another point as an example. Take this point here at the very top. That's 0, 6. And this point then turns into 0, -6. So we can see that this graph A, because this is graph A, this is graph B, this is graph C, and this is graph D. Graph A is done by central symmetry. Now, the next one is like a mirror image. We can see an F and an upside down F. Once again, draw a pretend axis in between, and you can see that it gets reflected. This one gets reflected 6 down, and then another 6 down. It meets its point on the other, its image on the other diagram. You can see the same thing here for this point here. Blue and blue, it gets reflected all the way down. So B is reflection in the x-axis, or axial symmetry. So axial symmetry refers to like a fold in it. So if I was to so as I was saying, number B is axial symmetry, because you can see that the symmetry here is that it gets reflected in the x-axis and goes the same distance down. You see that it keeps going, it goes to the axis, then the same distance down. So this is axial symmetry in the x-axis. Okay, now the next one, if we were once again putting a cross thread underneath this, okay, so just trying to put in a different color axis here. Green is always a good choice. Now, what we can see here is that all the points get moved across the same way. So let's take this red point here to this red point here. It goes down 1, 2, 3, 4, 5, 6, 6 blocks down and 3 blocks across. So it goes 6 down, 3 across. Look at every other point on the F. This one here drops 6 down and goes 3 across. So we can see that no matter what happens, all the points are doing the same thing. So this is known as a translation. A translation of 6 down and 3 across. And finally, the last one, if I was to take this F here so. Okay, we can see what's happening here. So as I take this here, and what's happening is, if we were to rotate this, it still wouldn't fit in, would it? So we gotta figure out what we're doing. Now we can almost see a reflection in the center. If I was to put a center line in between this, like so, you could almost see a reflection in a line. That, like this red dot, gets reflected and then brought back down again. This blue part here will come across and get reflected. So it's reflection in a line. It's axial symmetry. But it's not getting reflected in a vertical line, it's getting reflected in a diagonal line. Okay? Question 13. The points 2, 3. Points 2, 3, 10, 4. So 2, 3 being here. 10, 4 being there. 12, 9 being here. And then finally 4, 8 being here. We can see we're just after constructing a parallelogram. Like so. And it goes plot on the coordinate plane A to B, B to C, C to D. So we have A, B, C, and D. There we go. Verify that one pair of opposite sides are equal in length. So opposite sides would be AB. I want to show that AB equals DC. Or I want to show that AD equals BC. Whichever one comes to mind, okay? So what we have here is our points. So we're going to use the distance formula. Okay, so we're going to look down for the distance formula. So what we're going to do, AB, so x1, y1, x2, y2, and then DC, x1, y1, y1, x2, y2. So the distance formula being the square root of x2 minus x1 squared plus y2 minus y1 squared. Distance formula turns out to be 12 minus 4 squared plus 9 minus 8 squared. Put that straight into the calculator, exactly as it looks. 12 minus 4 squared plus 9 minus 8 to be squared. You get root 65. And then the other one, which is D as well, ends up to be the square root of, and this is, the first one was CD, or DC is what I did first. That's DC. Now I'm going to do AB. AB is going to be 10 minus 2 squared plus 4 minus 3 squared. That's also going to be root 65. Hence, they're both the same length. So, by finding E and F, the midpoints of AC and BD respectively, verify that the diagonals of A, B, C, D bisect each other. So, which are the midpoints of AC. So, what I have to do here next is I have to find out what the midpoint of AC is. So, A going all the way over to C here. Okay, so what we can say is AC being x1, y1, x2, y2, midpoint formula being x1 plus x2 over 2, y1 plus y2 over 2. So we can say it's going to be 2 plus 12 over 2, which is going to be 7. Then y1 plus y2 is going to be 3 plus 9 over 2, which is going to be 7, 6. So there's 7. 14, so 12, 7 on the x-axis, 6 on the y-axis. That's your midpoint right there, 7, 6. Okay. So that's the midpoint of that one there, is the midpoint of AC. Now we're going to go for the midpoint of ABD. Here we go there. So midpoint of AC being 7, 6. Midpoint of BD we're going to work on now. So BD, x1, y1, x2, y2, same formula as last time, x1 plus x2 over 2, y1 plus y2 over 2. So b plus 10 plus 4 is 14, 14 over 2 is 7, and then finally 4 plus 8 is 12, 12 over 2 is 7, 6, so that's also 7, 6. So we see that it bisects them there. Now, what it also wants me to prove is that verify that the diagonals of A, B, C, D bisect each other. So, to prove that they bisect each other is going to be quite difficult because we have to prove the lengths are the same. So, what I now have to go about proving is calling this M. I now got to prove that dm, let's roll this out for a minute. I now have to go about proving that dm equals mb. Then I have to prove that am equals mc. So that's what I'm having to prove for this next question, okay? So, just grab this here and move it on. So prove that they bisect each other. Here's what we're going to do. Okay, so let's make a list for points. D being 4, 8. A being 2, 2, 3. B being 10, 4. C being 12, 12, 10. Or say 12, 9. Go back for a second. C is 12, 9. And finally M being 7, 6. So, what we're going to do each time is we're going to do the distance formula, and each time we're going to use M. So we're going to be using that as x1, y1 all the time. Okay, so it's going to be something minus 7 squared plus something minus 6 squared. So we can say first of all it's the length of AM. AM is going to have a 2 there and a 3 here. We're just going to be put that into the calculator. You're going to get 5 squared plus 3 squared, which is going to be the square root of 34. You want to prove that AM, which is this part here, is the same length as MC. So next point we're going to use is C. So once again, same deal again. Just going to rub this out, and then we're going to use C this time. C is going to be 12, 9. So this is going to be 5 squared plus 9, which means that when you put that in the calculator, the length of CM equals root 34 as well. So we're just after proving that the point M bisects AC. Bisecting means it cuts it in half. Okay. Next part after that, we're now going to look at BM and DM. Okay, so DM, which is here, is going to be, D is 4 and 8, so 4 here, 8 there. And when you put that into your calculator, you're going to get 9 plus 4, you're going to get the square root of 13. Okay, and then once we're done with DM, which is this purple patch here, we're going to look for this yellow line here, which should be the same length, which is MB. So we're going to do MB next. So same formula again, except this time we're putting in B, which is 10 and 4. And lo and behold, once again, MB, when you put that in, will also turn out to be root 13. So hence it does bisect them because they're all the same length. Can you conclude that ABCD is a parallelogram? Give a reason for your answer. Is it definitely a parallelogram? It is a parallelogram because the diagonals of the quadrilateral bisect each other. Okay? So in parallelograms, what you have here is you'll have two. When you draw one diagonal to the other diagonal, and the second pair of diagonals, when you join them together, what happens is you end up getting a common point in the middle here that bisect each other. So what you can say is yes, because the diagonals in the quadrilateral just means a four-sided object. The diagonals in the four-sided object bisect each other. And that's a general rule for them.